good afternoon, ladies and gentlemen. I'm Steve Cheney. I'm the Chief Executive Officer for the American Security Project. And I hope I see a lot of fusion raving fans out here. For those not familiar with the American Security Project, we were founded in 2006 by Senators Hagel, Kerry, Hart, and Rudman. And their thought at the time was to take on topical issues from a national security perspective. And of course, one of those was energy security, and it's been one of our plank issues ever since 2006. And where we come down on energy security is a national security concern for us. And we built a board comprised of Republicans, Democrats, businessmen and women, and about 7 or 8 3- and 4-star flag officers from all the military services who could lend a perspective of national security to each one of these issues. So because of that, ASP has developed a long-term interest in fusion energy. Not that we're opposed to any other sources of energy, but they all seem to have certain drawbacks, and I'm sure you're familiar with what they are, whether it be coal and the pollution, or carbon burning fossil fuels, or even nuclear energy. And when you look at the spectrum, some are worse than others, but we tend to believe that fusion might be the long-term solution to our energy problems in this country and perhaps the world. One of the long criticisms of fusion energy is then it's going to take 30 years, and they've been saying that for 30 years. But we feel at ASP that it would take a lot less if you applied the necessary resources to get it done. I like to say that the science is proven, but the engineering is not. And people would go, how can the science be proven? I said, look up in the sky and you can see the sun, and we know fusion works. The problem is trying to replicate it here on Earth and make it into a power source. For those not familiar, and we're going to get a pretty good education on it today, fusion energy can be safe, secure, and sustainable. And we think we've developed a plan, and we put it out to the community where if you contributed about $30 billion over 10 years, you can get a demonstration plant within 10. And thanks to that and some impact or put in from our government, we think we can get fusion really down the road. Fortunately, the government signed up in 2006 to support ITER, which is why we're here today to talk a lot about the ITER. The Office of Science Fusion Energy Science Program received $505 million in the recently passed omnibus legislation, and $200 million of that is going to ITER, I think, in the 14 budget. And this ITER is in South France, and Dr. Sauthoff is going to talk about that here in a minute. ITER is important for a variety of reasons. Now, I sit on Secretary Kerry's International Security Advisory Board, and I was talking with our fellow on public diplomacy today, and ITER is indeed involved in public diplomacy, because when you look at a project that involves the United States, the EU, India, Russia, South Korea, Japan, and China, all contributing, and in many cases contributing more than we have to this project, and truly is an international project and an important one. And it's making great strides and great progress, and we'll get a good update today. I would hate to see that any of that funding ever got cut. And in fact, we at ASP feel just the opposite, that we ought to be investing in this project when we certainly know that many of our partners are investing in it as well. It's a critical test of how the world views the future energy sources. And when you look at China and the problems they have with pollution and burning of coal, they are investing in fusion energy, and it's important, and they want it to succeed as we do. George Will had a great column last month in the Washington Post, and here's a quote: "Given the societal will, commercially feasible production of fusion energy is possible in the lifetime of most people now living," and we think you can do it in a lot shorter time than that. And then he went on to quote some of our work at the American Security Project. He said, "To bring about a working fusion reactor in 20 years would cost about $30 billion, approximately the cost of 1 week of U.S. energy consumption." So as you can tell, at the American Security Project, we are what I call raving fans of fusion, and we will remain so. We're hoping, of course, that the funding continues, and certainly those on the Hill would understand that. We're really pleased today to have Dr. Ned Sauthoff. He's the director of the United States ITER Project Office, and he has recently been to France. He understands it, he's seen it, and he's got a great presentation for us. So with that, Ned, Dr. Sauthoff, I turn it over to you.
Okay, well, thank you very much, Daniel Cheney. Well, it's a real pleasure to be here, and it's a pleasure to have the opportunity to talk about a really exciting project. So, just to start, I like this picture, you know. Not only does it have the sun, and I hope you can feel the warmth coming, especially on these cold days, but in fact, there's more of a story here than you would normally think. It's not just a picture of a sunrise over the ocean. If you look at that sun, back around 1900, there was a big mystery. The question was, where's the power from the sun come from? Okay? And so there was a related question of how long is the sun going to remain lit? And so there were various estimates done. And you've probably heard of this famous physicist by the name of Lord Kelvin. Well, he made a variety of estimates. One estimate had to do with, well, let's imagine it was made out of oil. Well, how long would it have enough fuel to keep burning, producing power at the rate that the sun produces power? Answer, a few thousand years. Well, that didn't agree with the biological and geological evidence. So what else? So then they had another model. Maybe it was just slowly contracting and it was taking advantage of the gravitational energy. Well, that came up with about 10 million years. Back at that time, it was thought that the sun was about 300 million years old. And so, well, 20 million or so was not enough. So something else was going on. Well, it wasn't until the discovery of a new way of burning matter that they really figured it out. Now, you remember in chemistry class, you start out with so many oxygens and so many irons on the left-hand side of the equation, and then you balance the equation by having the same number on the right side. Well, that's chemistry. Okay. What we're dealing with today is something which is different. You start out with hydrogen on the left side, and you have helium on the right side. And that is what our sun does. It transforms hydrogen into helium. And if you were to look at the sun and measure what is there, it started out almost all hydrogen. It's now about 2/3 hydrogen and 1/3 helium because that hydrogen has reacted and produced helium. Now, how do you manage to get so much energy out of this? You know, is it like burning hydrogen, like if you just take a bottle of hydrogen and let it burn with the oxygen in the air? No. That also would be limited in the sun to a few thousand years. What you need is a real game changer. And the real game changer is that if you have the reaction, not at the chemical level, but at the nuclear level, you can get 1,000,000 times more energy per pound of fuel. And that's the game, okay? We're trying to find a way to get 1,000,000 times more energy out per pound of fuel than you can by chemical reactions. You can imagine that's going to change the world. The next thing you see in this picture is the ocean. Well, guess where the fuel for fusion comes from? It comes from hydrogen. Let's see, H2O, that's water, right? So there's hydrogen there. And if you look at the fuels that are most reactive, like deuterium, you'll discover like 1 out of 300 of the water molecules has deuterium in it. And then if you want to look for other fuels, you can find other plentiful sources of other types of hydrogen, and I'll get into that. But what we have here is a source of fuel which could power all of humanity for thousands, if not 1,000,000 years. Okay? That would change the world. Also, all you'd need is water. And not a lot of water because you have 1,000,000 times more energy coming out per pound than you do in chemical reactions. So if you look at a power plant today, you have typically 100 rail cars show up every day to power this power plant. Well, do you know how much hydrogen fuel you burn in a fusion reactor to produce that same amount of energy each day? About 2 pounds. Okay. That changes things. Okay? You can now have a pickup truck show up every 6 months. You know, it's a different sort of thing. So let's move on. You notice back on that picture of the sun, it looked like a little fuzzy surface. Well, it turns out that's mostly the effects of fluctuations in the atmosphere and things like that. But if you put a satellite up there, this is the TRACE satellite, which is, I guess, is only appropriate in the House Science, Space, and Technology Committee meeting room. Let's talk about satellites and the sun and all this as well. Well, what you see here is that the sun's surface is not spherical, and it's also not calm. You can see things boiling up, bubbling like in your pot when you're boiling water. You'll also see these loops coming out of the surface. That is due to magnetic fields being generated because of motions in the surface of the sun. So you have various things looping around in the surface that generates a magnetic field. Out pops the magnetic field, and this very hot gas called a plasma comes out, you know, tens, hundreds of, well, let's say lots of miles, come out, and it moves around, and then these sorts of things actually lead to things called cosmic mass ejections, where these big blobs of plasma go shooting out, and if they happen to be aimed at the Earth, they disrupt power grids and things like that. But anyway, what we see here is a way of looking at the sun. Most of the sun is gravitationally confined. And that's why you can have fusion on the sun, is that it's confined by gravity. So this very hot gas is confined by the very strong gravity on the sun. And the sun has enough gravity because it weighs a lot, 330,000 times the mass of the Earth. And so that's one way of confining the plasma. Another way is don't confine the plasma, but have the reaction happen very quickly. That's called inertial confinement fusion. See a picture of it over there. And what we're going to talk about today is called magnetic confinement fusion, where we substitute for the gravitational confinement of the sun by using strong magnetic fields, like 100,000 times the strength of the Earth's magnetic field, in order to confine this very hot gas. And so the sun, in fact, pointed the way. It pointed out that fusion is an attractive reaction, 1,000,000 times more energy per pound, and that magnetic fields are a way of confining it. And so that's what we're going to talk about today. And so that's why today we're going to talk about a device called ITER, used to stand for International Thermonuclear Experimental Reactor. And you see the sun at the left, and you see a cartoon of ITER at the right. It's a relatively large device. It's about 30 meters tall and 30 meters wide. And you can measure it on a football field like at the Super Bowl. It's like the 30-yard line. Okay, so it's a relatively large device. And it is that large because you have to have a certain amount of volume per surface area in order for this reaction to sustain itself. And so it costs a lot of money, $20 or $30 billion. And that's why it's an international collaboration in which, as General Cheney described, we have the governments representing more than half the world's population involved. Right? Now let's just talk about fusion. This is that periodic table that you saw in high school chemistry class. And the chemical rules were, you start out with so many of one type element, and you end up with that many of that sort of an element. That's not what happens in nuclear chemistry. In hydrogen fusion, you start out with a hydrogen atom, and it transforms into helium. I'll show you how that happens. And this is to be contrasted with fission, which starts out with something like uranium, which is something heavy, and then breaks up into lots and lots of other things. Okay? Both of these are ways of liberating energy, and the reason for that is that these various nuclei strive to be in their most stable state, and that's the intermediate size nuclei, iron, lead, things like that. So if you start out with uranium, it turns out that it's more tightly bound if you turn it into lead or iron or something like that. And it's just like if you have a ball and you hold it on top of this table, okay? Here's one energy state, here's another energy state. But if you drop it to the more tightly bound state, you liberate the energy and you get the kinetic energy out. Well, we're doing this big time, okay? We're finding ways of going to more tightly bound nuclear states in order to liberate energy. And you can do it either by starting with heavy stuff and breaking it up into smaller stuff, or very light stuff and combine it in order to make heavier stuff. And so that's the fusion process. You start out with things like deuterium and tritium and turn it into helium. So that is, in fact, the reaction that is most frequent if you look at the various fusion reactions. And the game here is to take a deuterium nucleus, which is a proton and a neutron, and have it fused with a tritium nucleus, which is a proton and 2 neutrons. Easier said than done. The problem is they're both positively charged. And positively charged nuclei repel each other. Now, in order to get them close enough to fuse, they have to get to a millionth of a centimeter apart. Okay, 10 to the minus 12 centimeters. Now, if you take a positively charged nucleus and get it within 10 to the minus 12 centimeters of another, it has a reasonable probability of fusing, but it took a lot of energy to get it there. And that energy can either be provided in a directed way, like in an accelerator, but then if it doesn't fuse, and most of the time it doesn't, it'll just bounce off and you'll lose the energy. If you do this in a way that if it bounces off, you still have another chance at using that energy, then you have a chance of making a self-sustaining reaction. And that's why you have this thermal motion. If you heat up the gas to a temperature such that the thermal agitation that's going on there is enough to get these positively charged particles close enough together, then you can actually have them fuse. And if they bounce off of each other instead of fusing, so what? They have another chance to come in and try to fuse. So then it becomes a matter of how well they're confined. But the action here is to get these deuterium and tritium nuclei together, close enough together, 10 to the minus 12 centimeters, that they fuse and then break apart into helium and a neutron. Now, the energy that you get out is measured in a strange unit called electron volts, which is the amount of energy that an electron gains by falling through 1 volt potential difference. It's about 10,000 degrees centigrade or something like that. And if you just look at the energetics of it, about 3.5 million electron volts of energy comes out into the alpha particle, and about 14.1, so a total of 17.6 million out, and about 40,000 electron volts in. So let's see, 17.6 million divided by 40,000, that's about 450,000 gain. And it's that gain that we're trying to take advantage of. So what we have to do is find a way of efficiently having that energy, the 17.6, not only come out and produce electricity, but also loop back and heat up your fuel, keep your fuel hot. So the way you do that is you use this positively charged alpha particle and you just keep it in the plasma, which you would like to do because it's also confined by a magnetic field. And so it comes back and it hits deuterium and tritium, keeps it hot, another fusion reaction, and you get this feedback loop where the plasma keeps itself hot, all the while spitting out these neutrons, and these neutrons go and they hit the walls of your device. If you're clever about what you make the walls of your device of, and have something like a lithium coolant going through your coolant loop, you can then have a reaction where the neutron hits lithium and liberates tritium. You've now produced the tritium that you need for the fusion reaction, and you have another loop. So what we have here is the raw fuels of deuterium and lithium being burnt by being at energies such that these nuclei can get close enough together to fuse. This is not a new thing. This has been done before. Been done in magnetic confinement in 2 different facilities. The one at the left, Tokamak fusion test reactor, was at Princeton Plasma Physics Lab in Princeton University. Yes, Princeton. Okay, and it produced about 10 million watts of fusion power back in '94. And the Europeans had a device called the Joint European Torus, now called JET. and it produced, 16 megawatts of power in '97. The normal story is the US came first, and then the Europeans followed with a little more power. But anyway, these two devices are the only magnetic fusion devices so far which burn deuterium and tritium. But they produced power. So General Cheney said, just look up in the sky and you can see a fusion reaction happening. Here are two instances where people built a device to heat a plasma up to thermonuclear temperatures, and lo and behold, more than 10 megawatts of power came out. Now, if you look at the history, as a function of time, I hate to admit it, I was a graduate student back in here, and we were producing hundreds of milliwatts of power. Devices called symmetric Tokamak, adiabatic toroidal compressor, things like that. And then there was a series of devices that did not run in deuterium and tritium that produced some fusion power by deuterium-deuterium reactions, or you could calculate what it would have been with deuterium and tritium. But then came TFDR and JET, producing the 10 and 16 megawatts, and then the progression, which is faster than the progression of memory and solid-state devices as a function of time, that progression stopped. And it stopped for lack of investment in a facility. And so, at that point, the world decided, well, let's get together and let's build ourselves a device that can take the next step. And that's what ITER is. So if you compare TFDR and JET with ITER, you see that they produced roughly 10 megawatts of power, and ITER will produce about 500 megawatts of power, so that's a factor of 50. And it produced, the earlier devices operated for about a second, and ITER will go 400 seconds to 1,000 seconds, that's a factor of 400, so we have 50 and 400, about 20,000 now in energy per pulse. And the gain was about 1, and the Japanese have a similar device that doesn't operate in tritium, but it also has a gain of about 1 if it were operating in tritium. So you end up with Europe, the US, and Japan all having devices which could produce around a gain of 1, but ITER will go to more than 10, and that's because it'll take less than 50 megawatts of heating power to produce 500 megawatts of fusion power. So it's like an amplifier. You put in 50 megawatts of power and you get 500 megawatts out. And so that's a big change. Now here are some of the devices that exist now. You'll see in the United States, D3D in Ohio, California, Alcatar CMOD in Cambridge, Massachusetts, and STX in Princeton, New Jersey. Those are the major US facilities. There are lots of European facilities, but the one most like ITER is JET, and it recently underwent an upgrade to change the wall to be more so-called ITER-like. There's another device in Germany that also has a metallic wall like ITER. And then you see new devices in Asia. JT60, which is a success, JT60SA, which is a successor of the JT60, Japanese Tokamak SAT, is under construction. There's a device in China called EAST, and a device in South Korea called K-Star, Korean Star. And these devices are superconducting, so they go and they have long pulses. So you have a deuterium-tritium device, JET, you have physics devices of shorter pulse in the US and Germany, and then you have steady-state devices, the newer devices, in Japan, China, and Korea. So that's the world constellation of stars, so to speak. So let's talk about ITER. Okay? Well, how did we get there? Well, around 1985, there was a summit between President Reagan and General Secretary Gorbachev in Geneva. And it wasn't going too well. Since Geneva has a history of difficult meetings, I guess. But they did agree that they would jointly design a fusion reactor. And then in 1988, they had been joined by Europe and Japan. And so now you had the United States, Soviet Union, Europe, and Japan doing engineering design, doing conceptual design activities on ITER. And then around 1991, the Soviet Union turned into the Russian Federation, and we now had the same four doing engineering design activities through around 97, at which point the Congress zeroed out US participation in ITER, and the other three kept going until around 91, until around 2001, at which point they put out a final design report on ITER, which was then the subject of negotiations. And so in 2003, Korea and China joined, and in 2005, India joined, and we now had 7 members to the ITER negotiation. And we here see the signing ceremony of the ITER Joint Implementing Agreement. And so we can see Russian Federation, Korea, Japan. Here's Jose Manuel Barroso, who was on the front page of the newspaper this morning with Mr. Putin. Here we have French President Chirac. Okay, now we're getting into China, India, United States, and European Commission. So these were the signatories of the international agreement in 2006, which was subsequently ratified in 6 of the 7 members, and it's a congressional executive agreement within the United States, and we were off and running. So here's an aerial view of the ITER site recently. And so what you see is that there's a cleared area of land. It's about 30 miles north of Marseille, off the southern, near the southern coast of France. And you can see that it's actually becoming quite an interesting facility. The Tokamak itself will be in a building here called the Tokamak building, and there's an assembly building back here. That's where most of the nuclear activity will be. Here's the big concrete plant that was constructed in order to build all the buildings. It's better to manufacture the concrete on site than to ship it in by trucks. This is a building called the Pellet Field Winding Building, built by the Europeans, and that is because there are some magnets that are too big to ship. Okay, so they have to be manufactured on site, and so that building is for that. There are other buildings I'll show you that'll be coming up. Here's the headquarters building. This is the power switch yard that the Europeans put out. The US is putting an extension on it. This is close to the Tokamak. This is ITER itself. It lives in this stainless steel bottle, 30 meters by 30 meters. And that's like a thermos bottle. Everything inside that is really cold because they have superconducting coils. Okay, so it's things like liquid helium at 4 degrees Kelvin. And so you have to insulate that thermally, and so you do that with a vacuum. And so there are various tricks to keep everything cold. But India is building that big vacuum thermos bottle, and then the rest of the members are building other things. The US is building this big magnet through the center called the central solenoid, and we're also contributing superconducting materials to those big coils, and we're building a lot of this cooling water stuff out here. Anyway, the 7 members are building these parts in their countries and shipping them to France where they're assembled and then operated. So here's up close the Tokamak. You can see here's a person for scale. And the plasma lives in here. So it's about 1,000 cubic meters of plasma, which is at about 100 million degrees centigrade. That's how you get those nuclei to get close enough together. And they're confined by a strong magnetic field, about 100,000 times that of the Earth's magnetic field, produced by these magnets here. It's a donut-shaped plasma, so those are the magnets. Then outside are more magnets, and then the cryostat, and then all the support systems. If you just look at raw parameters, we'll produce about 0.5 gigawatt of power, and we're going to do it with less than 50 megawatts in to get 500 megawatts out. We'll have 73 megawatts of power because you have to get the reaction started. You don't have the fusion power heating the plasma until the fusion reaction is started. So you have to have higher power to get it lit. And then you can turn down the heating power. Do it for periods of 5 minutes to an hour. Could go longer. It's just the cryogenic system and cooling ponds and things like that need to be bigger. producing reasonable loads, and you do it with about 15 million amperes there confining the plasma. That's to be contrasted with about 1 ampere going through your light bulb. Okay, so it's about 15 million times that. There was another recent development, which was the licensing for construction of ITER. This is the first time that, that a fusion machine like ITER has ever been licensed around the world. So it's a nuclear facility. It's not licensed like a fission reactor because it has nowhere near those risks. There's no meltdown. There's no high-level radioactive fuel. Okay? And so what you have to deal with here is the tritium gas, and you have to deal with low-level radioactive activation of the structural materials. So it is inherently much, much lower risk. Furthermore, there's no meltdown, runaway sort of event, because the trick here is to keep it going, not to figure out how to stop it. If something goes wrong, this plasma shuts itself down. Okay? And so it's passively safe in that regard. And so the real trick is to figure out how to keep it going. So if your control system stopped or something started overheating, you'd have some sort of a reaction to the plasma to shut itself down. And so the safety case was in fact challenging, but relatively easy compared to a fission reactor because the risks are so much lower. So here again is a picture of the site. We'll have more pictures. So here's where the Tokamak will live. If you look below that platform, you'd see 490 seismic isolator pillars. These are about 6 feet wide, about the size of a human, and the whole Tokamak building is built on top of these seismic isolator pillars, and that is to isolate ITER from earthquakes. So the whole building is sitting on these isolator pillars. It's like a rubber material that can move around in case of earthquakes. And that was because it's the responsibility of the host member of ITER to make an earthquake-free or limited earthquake environment. So the French had to pay to put in the isolators. Then if you look at the area next door, this is the assembly building where things will be put together before they're put into the Tokamak building. Here's that big magnetic field winding building called the Pellet Field Winding Facility. And you can see it here on the picture. Here's the headquarters building, and you can see around it are the representatives of the 7 members and the Director General and his team from the ITER organization. The U.S. delegation is over here. That's Bill Brinkman, who was the former director of the Office of Science. This is the Russian delegation here. That's Evgeny Velikov, who some of you may know. So what are the parties doing? Well, let me just describe for you. One of the biggest things that the parties have to do is to produce all this superconducting material. ITER has the biggest magnets, biggest superconducting magnets ever built, and so 6 of the 7 members are producing toroidal field superconductor for ITER. And here you see what has been produced in the different countries, just examples. This is the toroidal field conductor, which is niobium-3 which is a high-performance superconductor at high field. And it's a circular conductor about 2 inches in diameter and about 800 meters long, wrapped on a spool. So you can see that 6 of the parties have produced this. You can see that in Japan, they're producing not only that conductor, they're also winding coils. I visited the Mitsubishi Heavy Industry factory this summer, and it's a truly impressive operation where they make these coils. They also are producing some of the high technology radiation sources of microwaves, like 170 gigahertz gyrotron. Japan, Europe, and Russia are all producing these so-called gyrotrons. And to see the size of these magnets, here's one sector here, okay, which is this little piece of the overall magnet. You can see the size of that sector relative to a human. The Europeans are also producing toroidal field coils. The Europeans and the Japanese get those spools of superconducting material from the 6 members and then turn them into magnets. The Europeans are also working on neutral beams, and they're building a test facility at the University of Padua in Italy, and they're going to be testing some of these neutral beam components, which the Europeans will then put onto ITER. The Indians, as I mentioned, produced that big 30 meter by 30 meter thermos bottle called the cryostat, and they are busily making these pieces. It has to all get welded together at the ITER site because it's much too big to be shipped. So they are building a building in which they will put all this together. And then you can see an Indian electrical technician working on some of the high voltage power supplies for the diagnostic neutral beam system. Here's a Korean product. Turns out that the vacuum vessel that contains the plasma itself is being built jointly by the Europeans and the Koreans. The Koreans build 2 vacuum vessel segments and the Europeans build 7. So here are some vessel segments being built in Korea, and here is a power converter system for which the Koreans are responsible. The Russians also are producing these gyrotrons at 170 gigahertz, 1 megawatt, and they're producing another sort of a superconductor for the colloidal field coils. And in order to get some practice runs with their winding machines and the like, they made some samples out of copper. And so here's called a copper dummy conductor, which the Russians have fabricated and are about to turn into a coil. In China, they're also making these colloidal field conductors. Here you see it being put on the boat. It came out of their research facility of the Academy of Sciences of China in Hefei, and here it shows up in the ITER organization in that big colloidal field building. So that's what's being done around the world. What's happening in the US? Well, these are the components for which the US is responsible. The 2 biggest ones are the central solenoid, which is the magnet through the center, and that's the world's most powerful pulsed superconducting magnet. It changes its current throughout the pulse in order to induce a voltage around the tokamak. And by changing that voltage, by inducing that voltage, you drive those 15 million amperes of current through the plasma. The other big one the U.S. is putting, and that's about $250 million, something like that. Cooling water system is closer to $400 million, and that has the responsibility of taking the power out of the plasma, taking it out of the surfaces that the plasma sees, and it takes the 500 megawatts of power out and delivers it to the Indians, who, through a heat exchanger, take it out to their cooling towers and the like to exhaust the power. So those are the 2 big ones. We also produce our share, 8% of that toroidal field conductor that I told you about before. We produce a thing called a pellet injector, which is used to fuel the plasma and to stabilize some instabilities. We have a disruption mitigation system that I'll show you that shuts down the plasma if it starts getting out of control. We provide 75% of the steady state electric network, which takes the 400 kilovolt power off the grid in France, brings it down to power the facility. Instrumentation, 9 cyclotron transmission lines. Adam, you can give a lecture on 9 cyclotron. Electron cyclotron blankets and pumps and the like. And Savannah River National Laboratory is responsible for our part of the tritium handling system. So we have a partnership here. Oak Ridge National Labs is the host for the US ITER Project Office, and we have partner laboratories, Princeton Plasma Physics Laboratory in New Jersey, and Savannah River National Laboratory in South Carolina. So here's how some of the core systems are distributed. Again, you've got that spark plug central solenoid through the center. We're producing superconductor for some of the coils. We have various plasma-facing components we've designed and tested. And working our way out, we have that big cooling water system, and we have a variety of systems that heat the plasma. So let's look at that central solenoid first. Its field is about 13 Tesla. How to compare that? About half a Gauss is the magnetic field of the Earth, and this is 130,000 Gauss. So that's about 250,000 times the Earth's magnetic field. And it's a pulse magnet in that you start it with the current running from top to bottom, and you end with the current going from bottom to top. And it's that changing magnetic field that induces the voltage around the plasma. If you were to use it as a magnetic storage device, purely to store it, it stores about 5.5 billion joules of energy, a joule being a watt for a second. Right? And if you note that it costs that much to store 5 gigajoules, that's about 5 seconds of a major power plant's output. It's hard to store electricity with such magnets. If you look at the size of these things, you can see the man there. We're using conductor that comes from Japan, and then we're winding it into 6 of these segments, each of which is about 6 feet tall and weighs about 100 tons. So the whole thing together, there are 6 of them plus the support structure is about 1,000 tons. The whole Tokamak itself is about 23,000 tons. So this is about 4% of the weight of ITER. And if you look at the companies involved, the main contractor for fabricating the modules is General Atomics in La Jolla, California. And then for producing these support columns, we have 2 prototypes that we've made with 2 different companies. Here's the General Atomics central facility, but they bought a building in Poway, a little bit north of La Jolla, for actually doing the manufacturing. They had to jackhammer out all the concrete because the floor wasn't solid enough to move around these 100-ton modules. And so they've now made a very solid and flat floor. The reason it has to be flat is that they move these 100-ton modules around on air bearings. Okay, and if there's a slight tilt, you could have this 100-ton thing moving along. You don't want this to happen, okay? And so you want this to be nice and flat. So they produced that engineered surface, and they're now setting up the fabrication machines. For example, we have robotic insulation machines for wrapping the conductors with the insulator. We have a furnace that's about to be delivered, and that's for taking the niobium and the tin strands that are wound into a coil and having a chemical reaction occur that turns it into the superconductor niobium-3 tin. In order to do that, you have to heat this 100-ton coil at 650 degrees C for several hundred hours. Okay? It has to be very, very well controlled. And so that's what this reaction furnace is, or heat treatment furnace is about. Again, as I told you, these coils move around on air bearings, and the winding tool itself is being built in Italy by a company that has demonstrated superior capability in winding machines. The toroidal field is the one that's being wound by Europe, in our case. And we had to produce about 40 tons of niobium-3 tin strand, and then turn that into a rope, about 1 inch in diameter, and then put that rope in a stainless steel tube called a conduit. The way we started out is we had contracts with Luvata Waterbury in Waterbury, Connecticut, and Oxford Superconductor in Carteret, New Jersey, and they jointly produced reels of 40 tons of superconducting niobium and tin strand. That then was delivered to a company in New Hampshire called New England Wire Technologies that turns these strands into ropes. And the reason you make them into ropes is that you don't just want winding strands, because then you will trap superconducting flux between the loops. You want a very twisted structure so that it never builds up very much accumulated area. And so they go through a process of multiple rope making until eventually it gets out to about 1 inch in diameter. And then they put it into about 1 inch thick stainless steel round tube. So here we have the rope. That rope then goes to Tallahassee, Florida, where there's a small business that was created. There's a spin-off of the National High Magnetic Field Laboratory at Florida State University. And if you fly into Tallahassee Airport, you'll see a building, and then 800-meter tube, and another building, and that is where they do the jacketing for the US ITER conductor. And it's because you have a nice, flat, straight surface right next to the runway, okay? And so you bring in the materials, put it into one building, it goes through the tube, they wind up the final product at the other end and ship it out. So at this small company called High Performance Magnetics, they put the superconducting rope, superconducting material rope, into this jacket, smash down the jacket to support the rope, and then ship it off to Italy. We also are making a cooling water system, as I mentioned. This is at present a contract with Arriva Federal Services in Charlotte, North Carolina. And again, its function is to remove the heat from the fusion reaction and other sources. It can also drain the system, control water chemistry and the like. But it's got about 20 miles of pipe involved in it, and about 230 pieces such as tanks and valves and pumps and pressurizers and chemical control components and the like. And so we eventually figured out that if you're going to put all of the water equipment into your house, you buy the water heater and the sinks and everything here in the US, but you don't prefabricate the pipes in the US and then ship them to France. You know, what we do is we have a vendor in France that plumbs it together, but the US is building these 230 high-tech pieces of equipment. Here is the on-cyclotron transmission lines Adam. Okay, Adam got his PhD at Princeton doing ICH stuff, right? Okay, so what we're trying to do here is to deliver about 20 million watts of power to ITER in the range of about 50 megawatts. Now, why 50 megawatts? Turns out that the orbit of ions in the plasma around a magnetic field is that it spirals along the magnetic field and it circulates about 50 million times per second. And if you have a radio wave that's also going at that same rate, you can relatively efficiently transfer energy back and forth between the wave and the particle, and that's how you use that wave to heat the plasma. And you can get a lecture from Adam about how that works. Okay, and so we're responsible for the transmission lines. The source of the power is coming fundamentally from India. They're producing the radio waves. We transmit them, and they then go into antennas, which are produced by combinations of Japan and Europe. The electron cyclotron system is similar, except the electrons move a lot faster because they're a lot lighter, and so they go around about 170 billion times per second, and so you have to have a much higher frequency wave. And so, you know, your microwave is about 2.5 billion cycles per second, and this is 170 billion cycles per second. So it's a higher frequency, but the same sort of thing. And again, you can heat the electrons by resonating with their motion around the magnetic field. And so we're producing components for transmitting that power from the gyrotrons, which are produced by Japan, Russia, and Europe, to the launchers, which are produced by Europe and Japan. We're also producing vacuum systems, for which we have about 5,000 things that have to be pumped around the Tokamak facility, and so we're providing all those pumping systems. We also produce pellet injectors. Now, this is a little story, okay? How do you fuel a plasma? Okay? You just lob in gas, or what do you do? Well, it turns out if you just blow gas at a plasma, it tends to bounce off. And the reason is that it gets ionized, and then it's very energetic, and it's just half the time going to fly away. And so you have to find a better way. And so the proven way these days is you shoot in a frozen pellet of hydrogen. So you take something, since we're in France, let's say the size of a wine cork, okay? And you shoot it in at about 300 meters per second, and it penetrates part of the way into the plasma. If you inject it from the inside, the high field side of the magnetic field, in toward the plasma, it gets jet propelled by that magnetic field gradient, and so it goes in even further, and so this is called high field injection, high field side injection. And so we at Oak Ridge have been building these pellet injectors for many decades, and so we have the job of producing a variety of these. Some of them are for fueling, some of them are just burping the plasma. What do I mean by burping? Okay, it turns out there are certain instabilities in the plasma where if the gradient, if the sharpness of the edge gets to be too steep, then you can get some waves build up and spoils confinement in various ways. And so what we try to do is to avoid that edge getting too steep. Well, one of the ways to do that is to tickle its edge with like 40 times per second frozen hydrogen pellets. And so we do that also with pellet injectors, which shoot in, we have 2 of them each at 20 cycles per second, shoot in relatively small pellets to tickle the edge and stabilize the modes. Now there are heavier duty pellet injectors for things having to do with disruptions. So if you see the plasma is about to go out of control, and this is a normal event, you know, what do? Well, you don't want to have it go and deposit all its energy in the wall in one spot, and you don't want it to produce various runaway energetic electrons, so you try to kill the plasma gracefully. Well, the way you do that is you poison it. And you poison it by putting in a lot of neon or argon such that it radiates visible light and ultraviolet light so that the temperature of the plasma coasts down controllably. And then the plasma becomes more resistive, and then it dissipates the energy in the plasma and it goes away gracefully. Okay, that's the story. Well, you have to do that with these large pellet injectors, and so what you start out with is a plasma that's under control, and then you see that the plasma energy is being lost, and you say, aha, a disruption's coming, and now you want to kill it. And you want to kill it before it loses all of its energy, and you have a blip in the inductance that causes the heat, causes the current to go up, and then you get into trouble because it's now uncontrollable. So you want to inject it at a point where the plasma is still under control. And so what you do is you have your burning plasma, you see the so-called disruption coming, and then you want to intervene. Here are some researchers at General Atomics in San Diego studying disruption mitigation. I just throw this in to see what sort of things a fusion researcher does. It turns out fusion research is an international activity. This is done under the auspices of the International Tokamak Physics Activity. And you see a worldwide team at General Atomics where we'll see people from Japan, we'll see people from Europe, we'll see people from Russia, all working together on this disruption mitigation activity. You'll see it's like a control room in the Space Center, and you'll see everybody's looking into their screen, trying to control their device, trying to understand what's going on. You see a lot of young people, Lapis Nobu Asakura from JAEA, that's Larry Baylor from Oak Ridge. And these people are trying to, between shots, adjust the plasma so that the next experiment will teach them something new, and so that they can constantly be learning more and more about the plasma. And the US is a world-renowned expert in disruption mitigation studies and in disruption studies, and D3D has implemented many tools for monitoring and controlling disruptions, and that's why we're doing the experiment there. And then we from Oak Ridge have deployed these pellet injectors and these disruption mitigation systems on D3D to study how they work. And it's not just a US activity, it's a US facility being used by an international team of experts trying to study this phenomenon so that we can design the best system for ITER.
What language are all these people speaking?
English. Yeah. It turns out, I mean, the official language of ITER is English, which is great because it'd be really hard for us if it were not, okay? But the world fusion community speaks almost all English. If you go to the International Atomic Energy Agency meeting on fusion energy, which happens every 2 years, they don't anymore have simultaneous translation. It's all done in English. So English is sort of the universal language of fusion. We also have a responsibility for the tritium system, part of it. It is shared with Europe and Koreans. And in this case, what comes out of the pumps is hydrogen, meaning protium, deuterium, and tritium, plus the junk that got knocked off the walls. And so you have to separate the hydrogen from the junk. And that's the US responsibility in a thing called the Tokamak exhaust processing system. And so that is the responsibility of Savannah River National Laboratory. It's not needed for first plasma, but it's needed when you start using tritium. And this then feeds its output to 2 places. The junk, it stores or sends up the stack. The hydrogen, it ships off to the isotope separation system being done by the Europeans. And we chose not to do that for security reasons. And then the Europeans deliver protons and deuterium and tritium to the Koreans, who store it and then deliver it back to the US so that we can inject it as pellets, or to the Chinese, who can puff it in as gas. So that's the gas cycle. So the US is a part of this gas handling system. The US also produces a steady-state electric power network. This part of the network was provided by the European Union. It is the interface between the French grid, electric grid, at 400 kilovolts, and the ITER site. And the US will be putting into this location the part that steps down the voltage to more reasonable levels and delivers the power to the steady-state loads. There's a European supplied system and Russian supplied system for the pulse loads. And so we'll be delivering that in 2015, 2016. But it's more conventional electrical switchgear. We also are world-renowned for instrumentation. Normally, the US is a 9% player because that's the way it was all negotiated. Everybody's a 9% player except for the European Union, who's a 45% player during construction. And so normally you'd expect that we'd be providing 9% of the diagnostics. Well, we're producing 14%, and that's because when we were negotiating back in 2003, it was recognized that the US has a superior capability in instrumentation. And so we got more than our share of the instrumentation, and this is good, because this is how you see the plasma, and this is what the people want to do in order to study the plasma. There are really 2 things that you want to do if you're studying the fusion. You don't want to produce the big magnets so much. You want to control the plasma, and you want to measure the plasma. That's where the physics is. Okay, so we are involved in controlling the plasma through the pellets, the ion cyclotron, electron cyclotron, and the like, and we are involved in measuring the plasma. So we have positioned the US to be leaders in research on ITER. Well, where have we spent the money so far? Well, so far we've given out contracts and intercontractor work orders to labs and the like for a little over $500 million, and it's spread around 39 states. The biggest ones, California, and that's because of General Atomics in producing the central solenoid modules. New Mexico, that's because of Sandia in doing testing relating to the plasma-facing components. Tennessee, because we do lots of things in Oak Ridge. North Carolina, because of Riva Federal Services and the cooling water system. And then New Jersey and Connecticut for the superconducting materials. So, are we ready? Yeah, I'd say we're ready. Our materials, what we have to deliver is very well defined. We're no longer subject to lots and lots of changes in the design. We've signed arrangements for 80% of our components by value with the ITER organization, and we're ready to roll. We have about 350 contracts that have already been awarded. We have $1 billion in contracts yet to go. We're almost complete on the R&D and have completed the R&D for the first plasma components. Our 2 largest systems, the central solenoid and the cooling water, are in final design. In fact, now beyond final design. We had a final design review for the central solenoid in December and passed with flying colors. And we have a sound basis of estimate. We've gone through a variety of cost and schedule reviews with DOE, and so we understand the cost. And we've also found cleverer ways of doing the work, and so we found about $200 million in cost savings by doing things more cleverly than originally conceived. So let's just go back to this picture. So again, what we're trying to do is bring a star down to Earth, and what we're producing here is a plasma of hundreds of millions of degrees centigrade, or Fahrenheit, doesn't matter that much, factor 2. And we are demonstrating the scientific and technological feasibility of fusion. We're producing 500 million watts of power for periods up to about an hour. And we believe that this is establishing not only the fascinating science of self-heated plasmas and how do you control and maintain such a plasma, but also pointing the path toward a clean, safe, and abundant source of energy. And with that, I'll stop. Thank you very much.
All right, Ned, thank you. If you want to have a seat up here.
Okay.
We're going to open it up to Q&A. We only have a few minutes left, but I am, I'm ASP Senior Fellow for Energy and Climate, and I do everything on fusion and more here. But I want to first acknowledge the representatives we have from some of the ITER associated nations. The embassy, we have representatives from China, from Japan, from the European Union, and I believe from India as well. Yes. I wanted to first give them an opportunity to make a brief statement, say whatever they want or anything like that. So in no particular order, maybe we'll go and we'll have the EU go first here. So I can give you I have the mic here.
Thank you very much. My name is James Gadigan. I'm head of the science section at the European Union's delegation to the US here in Washington. I'm not familiar with the ITER file, so what I'm going to do is I'm just going to read you very quickly a statement which was sent to me by the European Commission for the purpose of this meeting. ITER is a first of a kind, the complete design and construction of a fusion device with the size of a conventional power plant. It is therefore an extremely complex project with important challenges in terms of cost, schedule and project management. Its success will, however, have a significant impact on the low-carbon energy mix of the future. ITER is already showing clear benefits for the competitiveness of the European economy, job creation in European companies, especially high-tech SMEs. At the beginning of September, Commissioner Oettinger chaired the second ministerial meeting of the ITER Council, which took place 7 years after the first ministerial meeting and the signature of the ITER agreement. The minister representatives were able to observe the impressive progress made in the construction of the Tokamak complex where ITER will be placed, and discuss the progress of the project as well as challenges inherent to such an extraordinary research enterprise. At the end of the meeting, the minister's representatives underlined the common efforts of the ITER parties towards the successful completion of ITER. Progress has been made in the past months for some of the most important elements of the project. For the Tokamak complex, this progress is visible from day to day at the ITER site. More than 1 million machine components, many of them first of a kind, are being manufactured by the 7 ITER partners around the world. These achievements are crucial and ongoing, even if they cannot be seen at the site itself. On the 20th of September, the first test convoy for heavy components from the port of Fos-sur-Mer in France arrived at the ITER site, an important milestone given that the first real convoys are expected this year, 2014. These achievements include also the decree authorizing the installation of ITER nuclear facility issued by the French Republic in November 2012 and the inauguration of ITER headquarters on the 17th of January last year. In addition, the Tokamak pit, hosting the concrete foundation and the seismic pads to support the Tokamak building, had been completed. The construction of the concrete base for the Tokamak is ongoing, and 2 major contracts for the construction of the Tokamak complex have been awarded. As for the other ITER parties, key components such as the vacuum vessel and the magnets for ITER are being manufactured by the industries, as we heard. Challenges and way forward. So while progress is being made, the project is nevertheless faced with implementation delays due to its complex nature, both from a technical and political point of view. There are uncertainties surrounding the current project schedule as part of the delays cannot be recovered and execution rate is not optimal. Therefore, in November of last year, the ITER Council requested a revision of the project schedule for the construction phase to be completed by June 2015, as well as an independent assessment of the project schedule to be carried out by a panel of experts with a view to improving schedule reliability. Besides building on the positive experiences of the unique ITER team created last year to enhance cooperation and integration between ITER organizations and the domestic agencies, ministerial representatives in September urged the ITER organization to produce and implement jointly with the 7 domestic agencies an improved management plan for the construction phase. The 2013 ITER Organization Management Assessment was submitted to the ITER Council last November. This is a regular 2-year exercise provided for in the ITER agreement. The management assessment that was conducted by the US independent assessor between June and September last year calls the ITER organization to take action in several areas to ensure a strong project management culture. Among others, it recommends to simplify the internal decisional process and organizational structure to ensure the right number of personnel with large project management and industrial experience, to reduce bureaucracy and to enhance internal and external communication. The assessor's recommendations are in line with the position constantly expressed by the European Commission in the ITER Council on the need to define a realistic schedule and to improve project performance in order to contain costs, which indeed must be a priority for the management of the project. And in response to the conclusions of the management assessment, the ITER Council called for firm initiatives in the form of action plans to be drafted by mid-January and endorsed by the Council at an extraordinary meeting at the beginning of February this year. At this extraordinary meeting, the IO's Director General will present the plans concerning the managerial and organisational matters, while the ITER Council will address a plan to improve ITER governance. These plans shall specify the timeline for the implementation and the indicators to monitor the effectiveness of their implementation. A project of the scale of ITER needs strong political commitment in order to succeed, in particular in a moment when work on the major components is underway and progress in the construction is becoming visible. And finally, I would like to finish by informing you that at the end of 2013, the Council of the European Union adopted a decision to provide the basis for the financing of the Euratom contribution to ITER for the next 7 years at 2.707 billion in 2011 values. I believe without doubt that this initiative shows the importance and commitment the EU attaches to this unique research effort. Thank you.
Great. Thank you. And maybe we can pass it right over to your
Let me make a very brief comment. My name is Akira Tsugitan and I'm the science counselor at the Japanese Embassy. I'm very honored to be here today. And I had a very good communication with the DOE people on this project. So first of all, I'd like to thank the US government for its firm commitment to the ITER project. And also, I'd like to thank the US Congress for its continuous support to the project. And of course, Japan will also continue to commit to this project. And I'm sure this is a great example of international cost sharing and international cooperation. So I really look forward to the further development of this project. Thank you very much.
Thank you. Would you like to say anything?
I think, my name is Jianping Wei. I'm a counselor for science and technology in Chinese Embassy. My colleague, Mr. Yugen, is honored and happy to be invited to attend these events. Thank you, and Dr. Sauthoff, and thank you, ASP, inviting us. I think it's science lessons for us and fusion. As we know, yes, I think we cannot only stand on our foot to face the solve the problem near our nose, but we should have a vision to look forwards and about the future, about next generations, maybe our next generations. I think there are climate change and a lot of things related to clean energy. Yeah, China is also handle these kind of problems. I think I should pay respect to all those scientists and their governments who are involved in this project. And thank you. I got there's some information about the ITER and progress and achievements here. I hope, because I'm not yet authorized to to give an official statement here, but I hope this kind of a partnership mechanism can be working smooth and effective in the future. Thank you.
Thank you. Do you want to make a statement? Yeah, sure. Thank you.
Good afternoon, I'm Varun Mahindra. I'm Counselor of Science and Technology at Indian University. I'd like to update the forum on the ITER activities which are undertaken at India. First of all, we are in constant touch with the Department of Energy. In fact, we have an energy dialogue starting in February where Mr. Moniz will be going, and he will be taking review of all the activities of ITER. India is developing the heaviest and the largest part of Tokamak, as you mentioned, a 30 by 30 meter of vacuum stainless steel bottle. And as mentioned, that this machine is behind the biggest scientific collaboration on the planet to deliver cheap, safe, commercial energy through atomic fusion. As the collaboration says that there are 7 partners and every partner is contributing 10% in kind and 1% in cash. So India is committed for that. And India is entrusted to make certain components which are cryostat vacuum vessel of ferromagnetic inserts, cryonic and cryodistribution systems, and everything you have been talking about that. And as this collaboration says that every country must have a development agency in their country to look after the progress of ITER. So we have a development agency in India, which is India Institute of Plasma Research in Gujarat. And I was in touch with the director of ITER, and he mentioned that the construction of 6,000 square meters of laboratory building within the ITER premises is complete, and that has been occupied, where they are making this patches of a vacuum bottle which will be shipped to the location to be welded there. And also the procurement arrangements are on track. Procurement arrangement for the diagnostic neutral beam power has been completed. The second, the PA for the vessel involved shield is also being discussed, and we are very much on track. So we are thankful for the consortia of the 7 countries which are taking initiative to look into the futures of the clean and the safe energy, and we are very, you can say, proud to be partner of this particular. Thank you very much.
Great. Thank you. With that, I think we've got just about 4 minutes before 1:30, and we have to let you go. So we'll open it up to Q&A. Wait for the mic to come around, and we'll try and be quick to get a couple in.
Yeah, hi, thank you. Creighton Jones, 21st Century Science and Technology. I was just wondering, particularly in light of the recent landing on the moon by the Chinese, and they've expressed interest in possible mining of the moon for helium-3, which could be, it's now considered 3rd-generation fuel for things like the Tokamak. Obviously the problem is it requires higher temperature, density, other requirements. But one of the ways to possibly mitigate that would be with polarized fuel. So I was wondering if, as part of the ITER, if there's any, they have in their periphery any investigation of polarization of the fuel to mitigate some of these other concerns. Thanks.
No, I'm not aware of any studies of polarization. The basic strategy for ITER is to find the easiest way to producing a self-sustaining fusion reaction, and deuterium and tritium are by far the most reactive. I remember I spent 35 years at Princeton. We did various collaborations with NASA about mining the moon, and there's an astronaut named Harrison Schmitt, as you know, and Jerry Kolsinski at Wisconsin, and a few others who are very strong advocates of this. And I believe that it is very important that we have a vision that we're going to be producing a fusion reactor that will get ever better, but quite frankly, we have to get ourselves up off the ground with something like the Wright brothers as opposed to the 747 as the first step. And so ITER is a good first step. It produces the heat. It demonstrates much of the technology. It doesn't produce electricity. It's just trying to study the physics and the technology for producing a fusion reaction. I'm sure there will be very many, very much better fusion reactors in the future, and polarized fuels give us one opportunity.
Hi, I'm Rare Fun. I'm a reporter at ClimateWire. Last year, the Senate Energy Committee sent a letter to the General Accountability Office saying that U.S. support for ITER is detracting from American domestic fusion efforts, noting that several Tokamaks in the U.S. are already idled and funding for inertial fusion has also been touch and go. So where does ITER fit in with respect to America's own fusion efforts?
Well, the answer is that both a strong domestic fusion program and ITER are necessary components. And so the trick is to find a way to afford both. We know what it takes in order to produce ITER, and we know what the domestic fusion program needs. And so we have to be effective in communicating that to the government so that they are supportive for those amounts.
Just to follow up, hello from French Embassy.
Oh, I'm sorry, I didn't know that you got it.
No, it's okay, it's okay. I just have to have your reaction about the recent aberration bill that was voted last week that says that the budget is reduced for the ITER project compared to the previous year.
Well, the language that's in the 14 appropriation is $200 million, but then there's about $22.7 million, which cannot be provided to the ITER organization until the Secretary provides assurance to the House and the Senate that adequate progress has been made on addressing the recommendations from the management assessor, which was mentioned by the European Union. It's my expectation that at this upcoming February Council meeting, there will be adequate progress made on those recommendations, and so this is not going to limit us.
Well, and with that, I think we've touched on everything we need to, and go to our website, www.americansecurityproject.org, to get more information on fusion in general, energy security, anything else on all of these topics. And thank you all for coming. And let's thank Ned for his great